Great pleasure and indeed a great honour to be able to introduce Roger Penrose and his title, From the Origins of Twistor Theory to Bi-Twistors and Code Spacetimes. Roger.
Well, thank you very much. Well, it's a great honour and pleasure for me to talk on this, my favourite subject. And, you know, the whole month, is it, of Twistors, or is it? It's amazing. And of course, lots of old friends which I'm encountering, which is very nice. I should warn them, but I can't see very well. My macular degeneration, when I look at them, they disappear, which is rather a nuisance. So please tell me who you are if you want to talk to me. That's great. Okay, now let's see. This gives you the subject of the talk. It's all about Twistor theory, and I hope I can get this gadget to work. So I wanted to explain how the subject came about and certain aspects of that which I'll come to shortly. And that's moving forwards. I should explain that basically the roots of the subject date back to 1961, was it? When I was at it was a sort of gathering of people on general relativity, including people like R.J. Troutman, I remember, and Arthur Komar and Engelbert Schucking, with whom I shared an office, and he was one of these wonderful people who knew everything and everybody. He was also rather original, which is an unusual combination. People who know everything and everybody usually think that they don't have any new ideas. It wasn't true of Engelbert. But the thing, I learned two key things from him. I remember that. One of them was that Maxwell's equations were conformally invariant, which I didn't know that before, which I found rather interesting and remarkable. And the other thing was that in quantum field theory, the key thing was the splitting of the field amplitudes into positive and negative frequencies. And I hadn't known about that before either. And the fact that it was the key thing, I think, was important. Not many people emphasized that to the extent that Engelbert did. And I thought that was wonderful. But what does that mean to say positive or negative frequency? Well, usually what people do is they split things into their Fourier components, and then you take the positive frequency and throw away the negative frequency. But the trouble with that is, with Maxwell's theory, Maxwell's equations have been conformally invariant. The Fourier decomposition is not conformally invariant. And so this worried me. So I thought, isn't there a way of expressing the splitting of the frequencies into positive and negative without knowing what the individual Fourier components are? And so I thought about this way of doing it, which is probably well known, but seems to me a good way to think about it, which is you think of a function. I'm talking about a function of one real variable, and that is defined on the equator to this Riemann sphere, and you imagine your function is divided on the equator, and that your function you think of as a holomorphic thing, and the boundary values are on the equator, and does it holomorphically extend into the northern hemisphere or the southern hemisphere, or neither, and can you split it into parts which extend one way and the other way? And this is indeed just the Fourier not Fourier decomposition, it's the decomposition into positive and negative frequencies. So this is a nice geometrical way of looking at that concept. So I thought, wouldn't it be nice if you could somehow, let's see what I've got on my next slide. I'm not sure I can remember what my slides say. Yes. Wouldn't it be nice if you could apply this sort of globally, this idea, to the whole of space-time? But the trouble with that, if you complexify space-time, and this is what this thing called the forward tube has to do with, let's not talk too much about that, I've more or less forgotten anyway, but it's a way of talking about positive and negative frequencies, whether it extends onto the forward tube or not. But it's only a tiddly little thing compared with the dimensionality of the whole space. There's not a question of a boundary dividing the thing in two. So that doesn't work. But for some stupid reason, I couldn't get rid of the idea. it seemed to me that there must be some odd way of looking at Minkowski space, which meant that the real things, in some sense, were on the equator, and that you had some extension into the top half or the bottom half, and those things that extended into the top half would give you the positive frequency. Now, why I had that thought, I have no real idea, but it seemed to me it was the thing that sort of kept nagging me that there should be a way of doing that. But as I have down at the bottom, the idea is not to think as points in space-time, but think of light rays. So let me come to that. And here we, in fact, have the sort of Twistor picture. On the left-hand side, we see a space-time picture. We imagine that as 4 dimensions. And a point is represented in terms of all the light rays passing through it. And the light ray is represented as a point. So if you think of light ray space, then you have the 5-dimensional space. Now, we see it's not really the boundary of anything as it stands. It's just a nice way of looking at things. Now, why did I think of this as a good idea? Well, the idea really came from, well, this was when I was in Austin, Texas, and I had a good friend, Ivor Robinson, who was an Englishman who the Americans loved because he had such a wonderful way with words. He never wrote anything down. It was always in words. So if he wanted to write a paper, he'd have to persuade somebody to become a joint author. But he did have great ideas too, not just words. And one of his ideas was to construct solutions of Maxwell's equations. You can imagine solutions which are based on null rays. People were very keen on null solutions, which null means that the principal directions point, well, both the invariants vanish, if you like. That's the simplest way to say it. And you have one null direction in which the Maxwell field points in a sense. And you have the congruence of these directions, and you have a shear-free congruence. And one of these easiest to describe congruences is you take a light ray and you think of all the other light rays which meet it, and that gives you a shear-free congruence. And so you could construct solutions of Maxwell's equations based on that light ray. But Ivor's idea was, why don't you displace that light ray into the complex, and the light rays which are trying to find it, they can still be real. So you have the light rays which are, in a sense, meeting that complex ray, and you still get a congruence of real light rays. They're still shear-free, but they rotate. And they can twist one way, left-handed or right-handed. And it seemed to me it was a nice idea to think of the light rays instead. But I had no idea, initially, what is the family of rays which meet null ray. I had thought about that for a bit, and I did realize that you could describe that family of rays in terms of Clifford parallels. I think I need to come to my next picture before I go into that. Let me do it. See, this is well, we've got that, a version of this picture on the heading of your notepaper, or whatever it is. This is a picture of Clifford parallels. So you imagine a 3-dimensional sphere, and the Clifford parallels, which I did know about, it's a family of great circles on the 3-dimensional sphere. It's a 2-dimensional family of great circles. They fill the whole sphere. They always miss each other. There are no intersections. They all link each other, and they make this wonderful twisting picture of linking rings. So you have to imagine that this picture, if you take a 3-sphere and you project it stereographically into 3 space, then the Clifford parallels in the 3-sphere project down to a configuration like this. So that was what there was, and we see the ring in the middle, and then there the straight line at the outside with the arrow on it is also a circle. It's one which goes through the point at infinity you're projecting stereographically from, and so it becomes a straight line. And I was aware that this configuration was in fact what the Robinson congruences did. That's to say, you take a moment in just a space-like slice of space. space-time. So you have one particular time, and then the direction of the light ray, if you take the family of all those directions, they're the tangents to these lines of this configuration. So I was aware of that fact, so I knew how to think geometrically of the Robinson congruence, and I realized that this thing somehow represented light ray displaced into the complex. But I didn't think too much about that. I think it was on a back coming, I won't go into the story because it's not part of the mathematics, but I did have the opportunity to worry about the dimensionality of this configuration. That is to say, how many of them are there? If this is a kind of complexification of a light ray, does that reduce the dimension? How many dimensions does it go down by? Well, light rays give you a 5-dimensional family, and I counted the dimensions of freedom of this configuration, and I realized it was 6. And to me, that was it. That's exactly what I wanted, because that gives you what the space, if the points in the space are represented by these gadgets, then the particular ones that actually give you the light ray, well, it specializes to the light rays meeting a light ray. So you can see how this thing specializes in that case. And then you go on to the underside, the negative twisting one, so you've got the splitting into the 2 halves, and it seemed to be doing just what I wanted. And I remember I was traveling back from a place where we were trying to recover from the Kennedy assassination. That was when it was. It's in late 1963, and when I got back home, I started to write this thing down in 2-component spinners, and it really came out so beautifully and elegantly that that was really what I would consider to be the origin of twistor theory. This is rather a lousy picture, I'm afraid, sorry about it, but I know people would have computer diagrams and all that, which look much better than mine, but this, I've lost all the colours. They do seem to, they should be there.
They
So, I don't know, the system seems to lose colours. I don't know quite why it does that.
No, there is.
Sorry?
He's got red and
Purple and purple, yeah.
Is that red?
And black.
Mine
Red,
are
black.
I think the N is red.
I see. Where's the sort of greens? I don't see any greens.
Oh, no greens. No, lots of greens.
Oh, I see. It's not my idea of a good colour picture, but never mind. Anyway, the whole big thing there in the picture is meant to be a CP3, complex projective 3 space, and a point then, well, you see a point in 3 space. Think of the one up in the top left. I don't know if I can point at it properly with this gadget. Let me try. Oh no, that moves it forwards, doesn't it? I don't move it backwards. No, that moves it. Oh, how do I go backwards?
Maybe magic can get you. Let magic move it from until you can. Yeah.
Is that moving backwards?
No.
No.
Why don't you let magic take you back to
What
where
do you
you
want to
are?
be?
Yeah,
That's
that's where you
good.
went.
That's good.
That's where you went.
I was taught how to do this just a moment ago. I am going C now. I was worrying about what was happening. Yes, that's it. Yes. Okay, thank you. Now to go for, at such that the buttons are quite different characters, the forwards and backwards. I would rather they look like each other. Okay, that's good. Okay, so this is the Robinson congruence or Clifford parallels or whatever you like, projected into 3 space. Now what is that in 4 dimensions? Well, you see a point. Yes, how do we represent a point? Well, you see up on the top left, and I don't, can I point to it without killing the picture? So the pointing is the, oh yes, it's the red one, isn't it? That's it. So that point up there, the green thing is the, yeah, press the red button and the green light. Okay, so it's up there. That is the point in complex projective space. What is that sausage through it? That sausage through it is a line, which of course is a Riemann sphere because we're complex. So it's really a Riemann sphere. So I've drawn it as a long, thin sausage to represent that it's got an extra dimension. But that line represents a complex line. So that sausage, that Riemann sphere, is a point in Minkowski space. That's right. So you want to see where it intersects the real splice, which is there. Those are the real light rays. And the intersection is this thing down here, which looks like a little circle there. But that really is the three-sphere. Have I got that right? Because why is it a three-sphere?
It's the hyperplane to get to the three-sphere.
Oh, it's the hyperplane. Yes, thank you. I'm forgetting myself. Yes, it's the dual. The dual of that point is this plane. That hyperplane meets the three thing here in a three-sphere. So that intersection is a three-sphere, and as that line wobbles around through the point here, it's a circle, it intersects in a circle. As you wobble it around, it makes this Clifford parallel circle all the way. So that is the vibration of the three-sphere here by the circles. Thank you. Yes, I was getting myself confused. So I need a plane here. The plane is dual to that point, and so each represents the other, and the plane then gives you, and the duality is with a 2-2. Never mind, I'll get to that later. Okay, so this, if the picture was better drawn, well, I can't really draw it because it's too many dimensions, but you get the general idea, I hope. Okay, so let's try and move myself onwards without moving myself backwards. Didn't move. Oh, that's because that's the pointer thing. That's it. Okay, you see, when I got back to where I was staying in Austin, I tried to write it down in two-component spinners, which is the things I was skilled with doing. And so, okay, the light ray, and here we have the light ray. That's the red one, isn't it? Yes. The red one is the pointer, yes. So that's the light ray. It intersects the light cone of the origin, say, that's the origin, in a point. And so you have one two-component spinner pointing along the light ray itself. Another one is sort of giving you the moment about the origin here. So you have these two spinners, what I tend to call pi and omega. The omega is the sort of the moment about the origin in a certain sense, and the pi, well, I should say, why is it pi? It's because it's really momentum. We'll come to that later. I don't think I had that notation at the time, but it is the way to think of it. It is really a momentum. And the pi, the omega is a sort of angular momentum, but it's part of an angular momentum. So it's giving you this sort of moment about the origin. So you have those two spinners, and this gives you a light ray. And if that's for a actual light ray, these things satisfy a certain condition. When it doesn't, when it's one of these Robinson congruence things, then you don't see the actual point, and the pi and the omega don't satisfy that condition together. Okay, let me try and move forwards. I hope I can do that. Okay, so that's giving you this bit of a messy slide, I'm afraid, but that is actually giving you what I was just saying. You have the pi and the omega, and they're both two spinners, and then you have the Z, which describes the twistor, which is pi and omega together, and the omega has to have an upstairs index and the pi the downstairs. It's a great shame that with my original paper, I had the indices the other way around. That's because I thought that pi was pointing somewhere, and things which point somewhere should have their indices upstairs. That's wrong. I didn't realize it was wrong until I realized the connection with momentum and angular momentum. My original paper had the up and down the wrong way around. And the trouble here was that Ed Witten, when he picked up on twistor theory, used my original paper for his conventions. And to me, it's the wrong way around. But still, see, often people don't worry about whether it's up or down, but I do worry about it's up and down, because with conformal transformations, it's important to keep straight whether the index are up or down. It's also important for the physics, because downstairs is momentum, upstairs is position. And so the pi, which is a momentum thing, really is the downstairs. And I have at the bottom how the pi's and omegas represent the position of momentum. You see P, you have to, I'm sure all of you guys know all this sort of stuff, but they have a primed and an unprimed index together. that makes me get a space-time index. And unlike in the old days when people introduced two spinors in an incomprehensible way, you just don't write down all those sigma symbols. As long as it's abstract indices, that's fine. It's absolutely rigorous mathematics. So your momentum P on the bottom left of this picture, that's it. You have your P, it's simply pi bar. And the two indices together, the unprimed and the primed index together, give you an ordinary space-time index. And so it is a momentum thing with a lower index. The angular momentum is a kind of mixture, pi's and omegas, but that gives you the angular momentum if you think of this as a photon. And it's also got a helicity part to it, which adds into the angular momentum. Okay, so that gives you the general picture. I'm sure all of you people know all these things now. Let me move forwards, if I can remember how to move forwards. There we go. That is, just gives you. So you see the two helicities right top half, one going one way and the other going the other way. And the points, the actual light rays, are the ones on the light ray space. Well, I thought this was a very nice picture, but the point I should make out here, which is really a key to what I'm trying to say in this talk. What is this describing? Well, you see, if I go back to the one description I was just talking about, which I hope I can do without confusing myself too much. No, I can't. Oh, that's the light. Make the slide go back. No, that's forwards, isn't it? That's backwards. That's it, yes. You see the definition of momentum, P and M down there, and they tell you what they are in terms of the two spinners. So that you see the twistor, which is both the pi and the omega together, give you the momentum and angular momentum. And that is really the most direct physical interpretation of a twistor. It's not a complete one because you've also got a phase factor which is not included in the momentum and angular momentum. So that's okay. Let me try and go forwards now. Forwards is this way. Yes. Yes. The point I was trying to make here is you've got positive and negative helicity. Now you see, this is a real puzzle. It's what I call the fundamental confusion. I can't read my slide. I hope it's saying the fundamental solution. The fundamental conundrum or paradox or whatever it is, the fundamental conundrum of twistor theory. You see, the whole point of what I was doing was to try and describe the description in terms of positive and negative frequency so that you could talk about quantum field theory or something like that, and then you needed to know, you had this lovely picture which tells you how the top half gives you positive frequency and the bottom half negative frequency. And we got this wonderful picture. But it's the wrong picture because it's not to do with frequency, it's to do with helicity. And so this is what I regard as the fundamental conundrum or paradox or whatever I've said up there. Confusion, is that the word? I can't read my writing.
Confusion.
Fundamental confusion of twistor theory. That it just gives you helicity, not frequency. Okay, of course it does eventually, but at this stage in the life, it was in a sense wrong. This couldn't really be wrong, could it? Because it works so beautifully in so many ways. No, that does move. Yes, here we go. Okay, now you see also here when I say there are different forms of twistor theory, of course people know all about this because they're probably using different forms of it here too. I tend to like to use the phrase pseudo-twistors. You see, the one in the middle are the real twistors, those are the ones I like to talk about, and the top and bottom ones are pseudo-twistors. I should say that pseudo is not an insult. After all, the whole of general relativity is based on pseudo-Riemannian geometry. It's a wonderful theory, and yes, indeed, amazing theory. The fact you've got pseudo in there is not an insult. It's just a description. So if I call these things pseudo-twistor theory, I'm just giving my opinion. I'm not trying to say it's an insult. They're wonderful subjects. But you see, twistor theory, as I described it, is to do with actual space-time, and the signature of that space-time is a key thing. And it's to do with the complex nature, which I thought it's lovely to have it complex, because I could talk about holomorphic things and where their singularities are and whether they extend one way or the other. So the complexity, and that fact that we're talking about holomorphic functions, is absolutely crucial to my way of looking at things. So the fact that the twistor theory, the twistor space, is a complex manifold was a key thing. Now you see, after Richard Ward made his wonderful construction for representing self-dual electromagnetic fields and so on, Michael Atiyah got very excited about all this. And but of course he picked up, and being a pure mathematician, he liked to have his spaces positive definite. And so it's sort of form of twistor theory, but it's pseudo-twistor theory. It's not the original kind of twistor theory. And I'm emphasizing that's by no means an insult. It's a very important subject, as far as I can see. People do lots and lots of wonderful things with this pseudo-twistor theory. Okay. And I'm not quite sure where the quaternionic aspect of this comes in theory. Perhaps people can explain it to me. But I guess the connections, it's really in some sense quaternionic. The field, which is complex for the normal space-time signature, and for the, well, you see, why do I say Witten? Because some of his work anyway, he liked to have space-time with 2 plus signs and 2 minus signs, whereas many people like to make it positive or pluses, and that makes things nicer in a certain sense because you can sort of see them all in a way. To my mind, it's sort of confusing the issue because it's not really quite physics. And if you want to do a Wick rotation, rotate your time axis back into space, there's something non-covariant about that, and it's not really, to my mind, a good way of doing things. It's nicer if you can express it without having to talk about such matters. So I should thought, yes, no, you should stick to the proper signature of space-time. But people often do consider positive definite. And what Witten was doing the opposite. He was making one of the space dimensions also like a time dimension. So you have 2 times and 2 space, and then the twistor space is real. And he wanted it to be real because he wanted to talk about delta functions and step functions and things like that. And then you can do that, of course, if it's real. It's a different subject, though. And if you want to change that into physics, you've got to be careful about what can change and what can't and all that sort of thing. So it is a different subject. It's worth studying, certainly, but it's not the same as what I was considering twistor theory to be. So it's another version of pseudo-twistor theory. Okay. Of course, we talk about general relativity in terms of it being Riemannian manifolds without remembering that it's pseudo-Riemannian, so that's all right. Okay, let me try and move forwards without going backwards, which is the course of the challenge. That's it, yes. Okay, now you see, this is where you start to get the frequency coming in, and it has to be with cohomology. So then you start to see, it took years and years to realize why it really did also correspond to positive and negative frequency. But it's a different thing. And you have to realize how to represent fields in space-time in terms of twistors. And it took a long time, several years, I can't remember how long it took, to realize it really was you're talking about complex analytic holomorphic functions of several twistor variables, and then you can do contour integrals, that was the first way you looked at it, on those variables to give you the real space-time answers. And what you're really doing then is you see here on the left, we have a twistor space, and you have a holomorphic function which has singularities, which is have 2 camel humps like that. And this is when you have a line. You want to know what the value of the field is. Well, this is in the forward tube, if you like. So you're taking well, I don't have to call it the forward tube. I guess no, I don't think it is the forward tube. Never mind. And if you take this line, sitting up there in the top half of twistor space, and so you want your field to extend into the top half so that it has positive frequency. And you do that by making sure that the places where it hits the singularities are separated, and as long as the camel humps come in two separate places, so they're separated in the top half, then however this line wiggles around, it meets it into two singular regions, which this is the line, which is really a Riemann sphere, and that line hits the singularity region in these two shaded places, and to work out the value of field, you do this contour integral around it. And I could do all these things, and I didn't quite know what I was doing at the time, and I remember, actually, when it came to the nonlinear version of this, and I was really confused, I remember talking to Michael Attia, and he straightened me out. I'm not sure if I'll come to that bit, but it certainly was an understanding that one was really, well, when one looks at, you see, you can go. Anyway, this is a way of describing positive frequency, is you have to have your singularities in a region which has two camel humps coming at the top. That seemed very odd, but then when you realize it's really cohomology what you're doing, you're thinking of the field, that line is where your where it intersects. That's representing the complex point we're looking at, and on the right-hand side you see the Riemann sphere and the two singularity regions, and you do contour integral which separates the two, and that works really nicely. But then I think it wasn't until after I talked to Michael that I realized that we were really doing cohomology. So you're looking at first cohomology, and that made a lot more sense than sort of having these camel humps and all that stuff. It looked very strange, but it really is looking at the that is the space-time version of it. You see the line going through, and you're now thinking not so much as where it's singular, you're looking at where it's non-singular, and that's that region between the two camel humps. It's the shaded region on the left side, and that intersects any line which cut. So it's in forward where you want it to be non-singular, the line's okay because it's all in the top half, and then you can do the contour integral to get the field. I'm sure you know all these things, so I shouldn't waste too much time on it. Let me move forward if I've got the right button here. So it's really first cohomology, and this is what you're doing. So to make it cohomology, you've got to do things like infinite subdivisions and all that stuff. And then I was told that for this sort of thing, you don't really have to do that. You can only go finite amount down. You can actually find one covering which gives you all that you need, and that's fine. Well, you might want to change the covering, but one covering will. Never mind. You only need two open sets in this case. But anyway, so it is splitting into two halves. It is positive and negative frequency. So it is right. But finally, after several years, I realized what I was doing was right in this rather strange sense. You're not looking at the functions being positive or negative in the top half or the bottom half. It's that the cohomology is in the top half or the bottom half. And that makes sense of it. So you can see the splitting now as being actually to do with the top half and the bottom half, and that does give what one was really aiming for all these years. Okay, let me try and move forwards. And this is a rather bad picture of what happens when you see, that was, I think, when Michael Attia helped me out a bit, that you can think of the splitting as sort of active, but none of those two halves just sitting there bearing a function, which is analytic on one side or the other, or both sides, really, and then modulo, ones which are just on one side or the other, which you're thinking of, actually, they're acting, the function is acting in a positive way to displace your twistor space. And you now glue two halves of twistor space, which has been deformed and moved away from the other half. And if you're preserving enough structure that it makes sense, then you can have a curved twistor space, which is this construction, and that's how you do things like the nonlinear graviton, which was the first example of this kind of thing, and that's fine. And people who don't know anything about cohomology often like to give this picture. This is an example of cohomology. You see, people say there's something wrong about the picture as representing an actual object in 3 space. Can you localize what's wrong with it? No, you can't, because you can put your hand over part of the thing and cover up any one of those corners. The picture becomes real. You can take your hand away and you start to make a whole picture. So you have a covering of this picture, and each covering is locally, makes a 3-dimensional thing. But where you've got the freedom, you don't know how far away from your eye it is, and so you need that freedom to make use of the cohomology, and the cohomology represents the impossibility of the picture. So it is really a representation in terms of the picture of what cohomology is all about. Of course, higher cohomology than H1s is not so easy to do. In fact, I put this as a challenge, didn't I? Because I think it's still a challenge. I've forgotten what the payment was. I think if somebody could find a nice geometrical picture that a layperson could understand, which represents second cohomology. And people kept coming up to me and saying, yes, I've discovered how to do it. And then I said, no, it doesn't.
You can't find it in Escher.
Sorry?
You can't find it in Escher somewhere.
Well, maybe. No, I've been looking. No, I've been trying to write this book about it, actually. Yes. If I'd seen it, I think so far, maybe it is there. I wouldn't be surprised. Actually, he did several things I'd never known before, like the Cantor set. There is actually a Cantor set in Escher. I'm not telling you where it is, but there is one. Yes. Okay, let me move on. Now, quantum. I want to say, when we make our twistors quantum objects, I can't remember where it originally came from. I think I had a paper in the International Journal of Theoretical Physics. I'm not sure if it was that one. No, there was another paper where I first introduced these commutation rules. You see, they're very obvious and natural. It's like the twistor, the canonical conjugate is the dual twistor, or the complex conjugate of a twistor. So one has an upstairs index, the other has a downstairs one. So it's just nice if you want to take their canonical commutation rule, AB minus BA, and then it's just a multiple of the delta function, which is fine. And when it's the same, they commute among each others. So the upstairs twistors are the canonical conjugates of the downstairs twistors. And if you go back and see how this works for the angular momentum, because in the special case where these things described, it's more general than this is more general than that special case. It also contains a little more than the commutation rules for angular momentum. There is something about helicity in there, as you see, an additional feature. But it is absolutely correct that when you translate this into the momentum and the helicity, you get, according to standard quantum mechanics, the right commutation rules, which tells you what sort of factor you should go on the right-hand side. It's just an H cross, I think, but that's fine. Okay, so that's the right. If you want to do twistor quantum theory, you do this. Okay, let me try and move forwards onwards. Now, what does the top line say? I can't even read it. Read my own line.
Real Bi-Twistors we have.
I seem to have jumped. I'm not sure whether the things are in the right order. What does that line say?
Relationship twistors.
No, that's not it. Let me go back. If I want to go back, I press this button, not the one that blows up.
There you go. Back to.
Yes. Okay, what I'm trying to say is Bi-Twistor. Actually, I'm not sure the slide tells you.
Real Bi-Twistors.
Yes, but I haven't said what A and B and C are. Let me tell you. I'll tell you in words. It's on the slide somewhere, but I think I got a bit muddled late last night. See, a Bi-Twistor consists of a twistor and a dual twistor. But they're not just any old twistor and a dual twistor. They have to satisfy these commutation rules. So you could imagine, well, you can have a downstairs the part of the Bi-Twistor, which is downstairs. It's attached to an upstairs Z, and the upstairs Bi-Twistor part which is attached to a downstairs Z. And so these Z's have the commutation rules given by this, and that means that the algebra has a non-commutative aspect to it because it's got quantum mechanics hiding behind it. That's this part of quantum mechanics hiding behind it. Okay, let me try and move forwards and fool myself. No, I'm moving backwards, aren't I? Now you see the A's and B's, that's what's slightly confusing. The A's were the coefficients. So the bi-twistor has A lower alpha times Z upper alpha, and that is the A part. Now for a real bi-twistor, the A bar, you see the A, I would have A without a bar on it. You see, I'd have to explain the notation. I'd have A with a lower index is one object, that's a twistor. The A without a bar on the upper index would be another twistor. That's right, a different one. However, if it's what you would call a real bi-twistor, then the lower one has the twistor conjugate will move the index into the upper position. So that A equals A bar means that the A, which normally has a lower upper index, is equal to the complex conjugate of the A, which normally has a lower index. So the notation is probably slightly confusing, but I just wanted to, I think that confusing partly because I'm not sure I've got all my slides in the right order here, but I've just said it here. So a bi-twistor has A's or B's or C's. Bi-twistor curly A at the bottom would have an A with an upstairs index, an A with a bounce downstairs index. That's a twistor and a dual twistor as the two parts. So it's an 8-dimensional object. And if it's to be so-called real, it means that A satisfies that relation I've got written up there. And see what I'm saying at the bottom, I can't explain what that is without going forwards. No, I've got them in the wrong order. Sorry about that. Let me try and move forwards, which is this button. Oh dear, what does all that say?
For the twistor treatment of curved spacetimes, one can use palatial twistor theory.
Yes. Yes, I'm putting this in. I think I was trying to sort my slides out last night and getting myself incredibly confused because, you see, I'd written an article which appeared in a book very, very late. I think it took several years before it came out. And in that book, I talked about palatial twistor theory. Now, palatial twistor theory is very much like bi-twistors. The difference really comes into what I'm going to say about in a minute. But you still have these up and down twistors in the same sort of way. But I don't think I would sort of have a term which I say a bi-twistor. But that's what I mean by it here. You have one of each. And it's an 8-dimensional object. So let's not worry too much about what that thing says here. But if you are talking about palatial twistors, there are things which are written in that article which do talk about how you can make curved space-times. And that's really the idea. So I want to try a somewhat different approach to the curved space-time, which I want to describe with bi-twistors. And I still have a good deal of time left. Good. Okay. Now let me try and move forwards, which is, I really haven't mastered this button business. Yes. Now you see in the bi-twistors, a way of talking about curved space-times is you see you have a system of coordinates, if you like, which give you one twistor and a dual twistor. And then you want to transform that. So you might be trying to patch things together in the same way as we did with the first cohomology. And you want to have one patch and another patch, and in the patching of one to the other, you want to preserve the appropriate structure. And that appropriate structure had to do with this form at the bottom, which I think is sigma. And sigma is that form where you contract the dual part with the twistor part with the dual twistor part. And that sigma form is a basic part of the structure. And if you want to go from one patch to another patch, you can do this using a generating function. The G is a generating function. So you take the Z's from one system and the W's from the other system. I should say that the W's would be the dual twistors of the Z's. And you can imagine them as being d by dz's. The W's and the Z's do have this canonical commutation relationship. So the W's are d by dz's, if you like. And the Z's are d by the W's, or minus. And that is the relationship between them. And if you want to go from one system like that to another one, you can do it with a generating function. And you take your G, which you take the Z's from one system, the W's from the other, and then you construct the other from the one and the way, and the sort of crossways way. And again, it preserves the form and it preserves the structure you need. And this gives you a patching of the palatial twistors, is what I was calling them now. So I thought I should mention this because that is a way of looking at curved space-times using these pairs of upstairs and downstairs twistors, but they have this quantum connection between the two. Since you've got generating functions to go from one to the other, it's not too harmful. I mean, you can see how to do it in a nice constructive way. Of course, you've got to make the generating function doing what you're interested in, which could be a real challenge. But you can preserve the Einstein equations and that sort of thing, and it really seems to work. Okay, but that's in this article which was published, I think, 2 years ago. I think the article was written about 4 years ago. I can't remember now. Okay, let's move onwards, if I can remember how to move onwards. Here we go. What does it say at the top? Can somebody tell me?
Twistor equation.
Oh, right. Oh, I must be near the end. Yes, I didn't talk about the Twistor equation before, but it's a good way of thinking about twistors in the context of conformal invariance. See, it's really the omega. I think of the twistors before were thought of as coordinates, if you like, for this twistor thing. I have an origin, and that origin I would know my omega and pi, and that would tell me my twistor, which may be hanging around out there somewhere. And the pi would tell me which way it's pointing, and the omega would give you the moments about that point. But if I think of it more in terms of omega by itself, then omega by itself I can think of as a field. And if I think of conformal invariance, that's the way to do it. Because if I do a conformal transformation on the original description, it gets complicated. Also, it gets complicated when you've got a nonlinear, well, I shouldn't say nonlinear, I'm not sure what the right word is, a general conformal mapping from one to another. But here, I could just do a conformal rescaling because that symmetric product, they're meant to be square brackets, I can't see them. No, they're meant to be
Round. In the Twistor equation, the green equation has round brackets. That's the way it's supposed to be. Symmetrization.
yes. But that's because the square brackets are 0.
That's right.
Have I said it right?
Yes.
No, that's correct.
The equations are given at the bottom. Yes, no, the round bracket. Oh, that's right. The equation with the round bracket is 0.
So what it
That's
says
right.
at
Yes,
the bottom is it leads to
Yes, sorry. I'm confusing myself.
Yeah.
The round brackets are 0, so the square bracket part is the whole thing.
Yes.
And so when you then take the derivative, then you see the answer is really a delta function, which should be there. I'm not sure I wrote the right one. Yes, it's an epsilon, isn't it? Yes, that's a delta. Epsilon AB is really, that's a Kronecker delta. If you've got one index up and one down. So that's a Kronecker delta times pi. That's right. So another way of saying, it's a good way of saying the Twistor thing is, because if you have a thing which splits in that way, then the omega does satisfy the Twistor equation, and it tells you what pi is too. And that derivative gives you pi and Kronecker delta. Now, how does this thing work in curved space-time? It doesn't, unless it's, well, I think even if it's conformally flat, Is there a problem with the equation? I've forgotten.
No, it's fine if it's conformally flat. It's if you don't allow it.
Certainly the equation's all right, yes. Yeah. So, but anyway, this enables you to do it when it's conformally flat. But what do you do if it's not conformally flat? Can you do anything? Well, I'm going to explain an idea which I only had 2 days ago. So there's probably a 75% chance at least that it's wrong. So you have to, in fact, I thought it was wrong when I woke up yesterday morning. I struggled with it, and I realized, no, I think it's all right, you see. But I think it is all right. But what we're trying to do is resurrect, in a certain sense, this formula at the bottom and make it, in a certain sense, more harmless. And we can do this by looking at the Twistor. I'm not sure whether there's another slide here. Go on, I'll try and see if there is one. Yeah, that's right. Except it's incomprehensible. See, I'm looking at the Twistor as the one part of the Bi-Twistor. So I've got a Bi-Twistor, and if I said that Bi-Twistor is real, then it means that the A part and the A upstairs and the A downstairs part are complex conjugates. Now, what I'm not sure I said, and what I'm saying it up here, is I can say it's null. I can talk about a Bi-Twistor being null by saying that the upstairs and the downstairs ones annihilate each other. So that's the formula at the top there. A downstairs contracted with A upstairs is 0. So that's what I'm calling a null Bi-Twistor. Now what I'm trying to do is associate the space of null Bi-Twistors with the space of light rays in a general curved complex space manifold, the Lorentzian manifold. Now, what I do now is I write down the formula for a null geodesic. I'm not sure whether that's written very well here. I think it's down near the bottom of the slide. You see, a null geodesic, if I think of, what have I got in the bracket? I've got omega bar, yes. Derivatives of omegas. You see, omega bar is a null vector, and I want to say that null vector gives you a null geodesic. To say it gives you a null geodesic would be if I take its derivative and I contract it with itself, then I could say that's 0. That would give me a null geodesic with an affine parametrization. So that would be a nice thing for a null geodesic. So I can write that equation down. Now what I'm saying is that equation is somehow, you see, I contract it with pi's, and then I just write it out. And what is it saying? It's saying that the Bi-Twistor, which has omega and pi as its parts, is a null Bi-Twistor. So what I'm trying to say is that the null Bi-Twistors correspond to null geodesics. And certainly in conformally flat case, you can see that's true. But what I'm trying to say is that in conformally curved space, maybe it's still true. And the thing is that the trouble with the Twistor equation, which we had in the previous slide, you're only using a little bit of it in making this equation work. And this is just the equation. So it's very close to saying that the omegas point along null geodesics. I hope I've got the omegas and pi's the right way around. Yes, the omegas point along null geodesics to say that in the Bi-Twistor language that it's null. In fact, it's just this equation here. And then I put some pi's in it, and I can make the pi's change around. So it really is just saying that the rest of the thing without the pi's is, well, the pi's come into the equation, so you have to be a little careful. See, that's not quite true. But anyway, it's a sort of idea without being fully worked out. The idea is that by looking at null twistors, the family of null twistors in a Bi-Twistor system, you can actually describe the family of null geodesics in a generally curved space-time, which is not conformally flat. It doesn't have to be conformally flat. I have missed out saying an important thing, if I've got a few minutes to say it. I seem still all right, I think. How many minutes have I got?
Yeah.
What I should have said about Bi-Twistors is I really worked these things out because I was supposed to be writing an article in honor of C.N. Yang. And the article was supposed to come out on his birthday, at which he would be 100. He's now 102, I think. So I wrote this article, thinking, what can I say? And I thought about the Bi-Twistors. And I thought, what can you do with Bi-Twistors? You can't very well multiply them together because you get things with the Zs. You start with just one Z and one dw Z, if you like. And if I multiply two together, I'm going to get ZZ and dwz. And if I multiply three together, I've got three Zs and all that. So I thought, well, there is a way of getting it done. What you do is you totally skew symmetrize. You take the complete skew symmetric product of three Bi-Twistors. And then you look at all the commutators. They all simplify right down to tell you, gives you a fourth element. So you have a totally skew product of three Bi-Twistors. It gives you a fourth. And I thought, I was trying to do this because I had this kind of feeling that split octonions should have a Twistor description somehow. Why did I think that? For a stupid reason that when you write out norm in terms of real mats, you've got a quadratic form with four pluses and three pluses and four pluses and four minuses. And that's nice and symmetrical, and it's just what you get in Twistor theory. A stupid thing to say, that means they're the same thing in some sense. But it turns out to be correct. It's correct. You take this triple product, which I'm saying in words, even if I haven't got it written down. I think I have got it written down somewhere, but I think I've lost it somewhere. No, it's in the paper. It's in the paper in honor of Yang. So you write down this triple product. It's like see, when Hamilton found his quaternions, you have the vector part, which is a product of two things, and it gives you another vector. Now, I'm saying that with the octonions, you're taking a product of three things, where now one of those happens to be chosen as your unit element. So you say, let's choose a unit element as a special element. And then the triple product, with the unit element as being one of them, is your octonionic product. Now you lose associativity, because the next time you're taking another triple. So it does lose associativity. You certainly lose commutativity. And if you play around with it, you see it actually works. It does indeed give you the split octonions. And this is what the article was describing. Now, I'm not sure what that's got to do with the other things I was saying, but it's rather nice that you have this triple product. It's sort of more important in a way than the split octonions themselves, because that requires taking a unit element. If you get rid of that unit element, then you've got this operation sitting there. It's just not an ordinary product. It's an operation on three things to give you a four. You can even think of it as an operation on four things, totally symmetric, to give you a scalar. That's true too. But you've got to be careful with the signs. So it's a little bit tricky. So that's just with three things to give you a four. And that's exactly what it does. And well, that's the connection with the octonions. The triple product gives you the octonionic, split octonion. I just want to make a conjectural comment at this point. You see that triple product, when you think of the space of the Bi-Twistors, well, objectively it's a seven-dimensional space. And then you've got these triple planes. So you've got certain planes coming from triple products of the three. And those planes don't, in a sense, care where those three initial vectors are. You can rotate them around. So the temptation here is to think that it's got something to do with strong interactions. See, in physics, you see, you've got some nice gauge groups and you've got some ugly ones. The nice gauge groups are SU3, which really works. That is an honest, genuine, you're looking at bundles. And people talk about quark confinement and all that stuff. Nonsense. You shouldn't get quark confinement because if they were there, it's like having a Mobius strip when you've got one edge painted red and the other one green. You can't do it. You go around the Mobius band, and of course that's the whole point about bundles, that you can't globally, necessarily, you can't globally do it. So in particle physics, you've got strong interactions which are a genuine bundle. The other genuine bundle I know of is electromagnetism, but then it's just a U1 bundle. Now, do you see U1s and SU3s in Twistor? Maybe, because you've got this triple product, and you also, in order to get the Bi-Twistors right, you have to introduce a circle to get things to work. So you get, in a certain sense, things which look a bit like the gauge theories in physics, which really are gauge theories. I don't know about weak interactions because that's not a genuine gauge theory. You've got W particles and so on, which shouldn't exist if it was a genuine gauge theory. So it's only an approximate one in some sense. But that's the sort of other question. Do Bi-Twistors have anything to do with particle physics? And I'm conjecturing that maybe they do. There was an attempt way back in Twistor theory's history to try and do particle physics with twistors. And I remember having an occasion where I visited Caltech, and I visited Caltech, and Stephen Hawking was there. This was a time when he could still talk. And I visited Caltech to visit Stephen. So I talked to him a while about various things. The conversation sort of ran out. And he said, is there anybody else in Caltech you'd like to talk to while you're here? And he said, would you like to talk to Gell-Mann or Feynman? Or I said, well, actually, even though I'd met Feynman before, I still said Feynman, of course. And so he said, okay, I'll get in touch with him. Stephen Hawking picked up the phone. I'm not sure, I think he could pick up phones and things in those days. Picked up the phone and phoned up Feynman's secretary. Feynman, I heard about this story from the other end, so I know it's true, not only from my version. And he spoke to his Feynman's secretary. And he was being Stephen, was able to get out of Feynman's secretary that Feynman was away on holiday. And what was more impressive about Stephen being Stephen was that he found out where he was on holiday, namely that he was at home on holiday. And he got his phone number. Who else could do that? But anyway, so Stephen immediately phoned Feynman and asked him to come round and talk to this chap here who was interested in discussing things. I was really trying to talk to him about particle physics and whether Twistor theory had to do anything to do with particle physics. The next day, Feynman did come around. He was in a pretty grumpy mood, not unexpectedly. And I noticed particularly that I'd sort of start asking him a question. And I wouldn't have finished the question. I'd be halfway through, and he would answer it. And he kept doing that. It's rather disconcerting to have your questions answered before you finish the question. The only snag about this is that sometimes he misconstrued what the question was actually going to be. And then it was almost impossible to dislodge him from what his view of what the question would be. But anyway, it was a very important. I tried to talk about particle physics and Twistor theory, and he said, don't follow up that route on particle physics. It will get you nowhere. He was absolutely right. That would get you nowhere. Now I'm trying to hope this is something different here. But I did describe other things on Twistor theory, and he said, keep going with that. That sounds like interesting stuff. So I thought that was quite very good advice I got from him. I think that's all I want to say. Is the time up? I think it is.
Well, thank you very much, Roger. Are there questions? Somebody at the far left at the back there. Hang on, Claude, I'm asking the back at the back.
Hello, Roger. It's nice seeing you again. It's been quite a while, actually. I think it's probably.
I'll have to see you.
I remember back in 1993 when I was
93.
93, when I was at Part 3 student here.
Oh, I see, yes.
Watching an amazing lecture you're giving on Twistor theory. First time I ever came across Twistor theory. I had this magnificent acetate with mermaids and castles and fairies and all sorts of weird and wonderful things I've never seen before given in a lecture. It was absolutely amazing. And it immediately got my mind going and thought, that's what I want to do. And a little while later, you kindly invited me on to chat about perhaps doing a PhD in Twistor theory. However, I ended up in Imperial. I suppose the cash were offered to me, and I ended up in Imperial for a while. But a number of questions I wanted to ask you, one of which, over the last 31 years, I've never actually remembered to ask you when we've actually had a meeting.
Maybe somebody solved it in the meantime.
Well, it's not really something that needs to be solved. It's basically, when did you come to the realization that Twistor theory might be the key between a marriage between quantum theory and general relativity?
Question, I'm not sure I do realize that. Well, you see, it was a strange thing because the original idea of the Robinson conferences and all that came about when I was at, as I said before, in Austin, Texas, the group that was sort of run by Engelbert Schucking, and I had an office there. The office next to me was Roy Kerr's office. Ray Sachs was down there, and there were a few other really distinguished relativity people. And I was there being supposed to be doing relativity theory. Now, you see, Twistor theory hadn't been thought of as such until this occasion when just after the Kennedy assassination, when I came back, moving back to Oshwa. And it was only then when I realized that the Twistor description in terms of two two-spinners, which was really the key thing. I couldn't write down what a Twistor was until I had the two two-spinners. So it was then. That was, you see, when did I realize it had any general relativity? Well, the question is, did I realize it had any general? Because I remember getting very taken with Twistors and trying to lecture it to people about it and try to talk to people about it. And most of them weren't interested because they were trying to do general relativity. And I couldn't do general relativity with them because it depended on the space being conformally flat, or maybe actually flat in those days. So the answer to your question is I didn't know at that time. Did I think it had anything? I can't remember what I thought. I probably did think it should have something to do with it, but only in a very roundabout way. Yes. I must have made some false tries of various kinds at that time. But you see, it was the natural thing to do because I was surrounded by people who were grouped together in this group in order to discuss general relativity. So since if I'm supposed to be part of the conversations, I should be expressing my interest too. I was interested because I think that wasn't too far from when I proved this theorem. It seems to have won a Nobel Prize eventually. So I was at the same time thinking about causality issues in general relativity. It was a sort of different activity at that time. I don't think I was particularly relating them. It's a hard question to answer. I have to try and remember what my mindset was in those days. I probably did have a remote feeling that it would connect, but I didn't have any idea how. Which is probably just as well, because I wouldn't have been able to at that time. It's a long way from it.
Good. Well, first of all, just a comment about your current fascination with the Cayley numbers. I wanted to remind you that, in fact, Cayley is your mathematical great-grandfather, right? Your direct descendant. He was Baker's. Oh. He was Baker's supervisor, and Baker was unsupervisor. But
yes, I think I did know that. Yes.
But in terms of Bi-Twistors, your ideas are actually very closely related to work that some of us did in the 1980s on Bi-Twistors.
Oh, yes,
So
yes, I know,
in
yes.
particular, you might look again at the paper by Rob Baston and Lionel Mason, was explicitly, and Lionel's sitting next to him. Explicitly uses the pairs of twistors, and the whole point is that so the thing that I had to sort out when I did my related work was that, so if you're working projectively, you're thinking in terms of P3 times P3 rather than C4 times C4, then the structure you get, rather than having a symplectic structure, it becomes a Poisson structure. And that Poisson structure which is kind of degenerate along the space of complex null geodesics. So there's a pairing.
Okay.
So in that framework, you can think of in a curved spacetime, you could sort of think of your Bi-Twistors as really being Darboux coordinates on P. But I don't know how to do any of this if the spacetime is not real analytic. That was one of the we made a lot of progress.
People often ask me what the connection with Bi-Twistors is, but I guess they needed to be known in the sense of.
Well, no. So the Bi-Twistor space. So the main theorem about the equations of general relativity had to do with you're looking at things which are you don't get P3 times, you don't get a curved analog of P3 times P3. You get an infinitesimal neighborhood of sixth order. So you can look at functions that are on P3 times analogs of functions on P3 times
Is it only sixth order?
It's only up to sixth order.
But then you can think of a theory which has a z dot w to the sixth term in it. So it somehow extends to all orders, but you start picking up errors after that.
Well, there might well be close connections between these.
Yes,
I wouldn't be at all surprised. But you see, even two of the things I did are close connections which I hadn't quite realised with the palatial twistors and the Bi-Twistors.
So anyway, I think you might try to pick Lionel's brains a little bit because he's had entire groups of people doing twistor string theory using Bi-Twistors and related things. So where these infinitesimal neighborhoods do come into it. So.
It'll be interesting to see the connections, yes.
Are there more questions? Okay, I'm not seeing any, so thank you very much, Roger.